Thank you so much for joining. I'm not sure where you all are coming from today, but if it's the middle of the day like it is here, thanks for taking your lunch hour to come learn a little bit more about hazmat. And if it's late at night or early in the morning, really appreciate you taking the time out of your free day to learn. My name's Mel Ebeling. I'm going to be kind of giving this presentation today. We also have Andrew Shanes on the call, who is another member of the WADM leadership for the SYP interest group. So if you have any questions for either of us, either about this presentation or how to get involved or what kind of opportunities we have, feel free to message us individually in the chat or raise your hand and speak up. Um, just a little bit about me so we can go ahead and get started. Like I said, my name is Mel Ebeling. I'm a resident physician at the University of Cincinnati, in the United States in Ohio. Before I became a physician, I was initially an EMT in the fire service, but through that role, had the opportunity through the U.S. Department of Homeland Security to get trained as a hazardous materials specialist, and it was something that initially I started getting into hazmat just for the sole reason of wanting to join the fire service, but quickly learned that I liked hazmat a lot more than fire, and so this is something that has kind of defined part of my career, and is super exciting to me because it gives you the opportunity to kind of combine chemistry, and emergency medicine, and all that kind of stuff. But happy to talk. We'll kind of on the spectrum of hazmat from like counterterrorism, the military side, to like industrial transport, things that you might see more in daily society. We'll probably focus a little bit more on the things that you're more common to see, just in your day to day. But happy to talk about either, or in any sort of like specific niche area of hazardous materials. So, going ahead and getting started, and let me make sure that my screen is shared here. Um, cool. Are you all able to see this? Can I get a thumbs up or a yes? Awesome. Thanks. So first, I have no financial disclosures to report. Some learning objectives for today is that this is hazardous materials is so broad. There's so many different categories, but I hope that just thinking about the fundamentals of this, we'll be able to talk about the various different classes of hazmat, how we can use physical, chemical properties to guide how we would respond to a hazardous materials incident. How do we recognize this out in the wild? What are some different labeling strategies, and guidelines that are out there that help emergency responders and us who are involved in disaster medicine get more, be able to recognize quickly that an incident has occurred. We'll talk a little bit about protective actions and PPE, and then just like briefly about different types of decontamination and stuff like that. So kind of our outline here for today, like I said, we'll talk about hazardous materials in general, what are the different types, the chemistry, the recognition, and then ultimately some response principles. So moving along into types of hazmat, I think it's important to start with just a definition of what exactly is a hazardous material. And there are so many different agencies, particularly within the United States, but I'm sure you'll find in multiple different like international agencies and in your own country that there might be some different definitions there. But from the NFPA, which is kind of what governs our fire service, who are the responders that are usually dealing with these incidents. They define a hazmat as a substance, whether that's a solid, liquid, or gas, or energy that, and the key word here is when released, is capable of creating harm to people, the environment, and property, and that includes weapons of mass destruction. So, like I said, I think the most important part here is the when released kind of clause. You know, we deal with hazardous materials every day. They are just our cleaning materials that we use. It is the gas that we put in our cars. It is the things that we do when we're cleaning our car, for example, different chemicals there. But we wouldn't exactly call them hazardous materials or classify them when it's a little bottle of just cleaning solution. But if that were to somehow get released from its container, whatever that may be, then in that case, we might be dealing with a hazardous materials incident. So, and like I said, there's a couple of different definitions, but most of them generally come down into this kind of definition there. And I think CBRNE is a great acronym for how we can think about the different types. Now, I know traditionally, for those who are familiar, CBRNE is something that I feel like we talk about within the context of counterterrorism medicine or on the military side of things. But ultimately, we can think about all hazardous materials as fitting into one of these general broad categories. So first we have our chemical hazards. I feel like that's the main one that we get a lot of focus on. And that includes things like gases, flammable liquids and solids, oxidizers, which can create really like unstable products and cause a lot of harm. We have corrosives, and then kind of switching a little bit more onto the military side of things, nerve agents, riot control agents, things of that nature. You're more likely to see in those environments. Um, Next, B for biological. This is our viruses, bacteria, and toxins. While I'm sure there are some biomedical industries that transport these things or work with these hazards within very controlled environments, particularly if you're involved in infectious disease at a federal level. I think a lot of these things we think about in the context of like man-made biological warfare, but those can definitely sort of present themselves. Next, we have radiological, and I will distinguish that between N for nuclear. But when I think about radiological hazards, of course, like there is radiation, believe it or not, that you are exposed to or that is present in your daily environment within the medical context. We have things like radiotherapy, which helps people who have cancer or helps with the functioning of certain devices. There is radioactive material in smoke alarms, for example. So there's a lot of useful ways that we can employ radiation in our day-to-day lives. On the opposite end of the spectrum, when we think about terrorism, you can have radiological exposure devices or dispersal devices, and those are kind of differentiated by um, one is a device that maybe is planted in a certain area and is releasing radiation, and maybe it's meant to target a person or a small group of people, versus a dispersal device, which the whole goal is to spread out radioactive material that may be inhaled or ingested and cause harm that way. Um, this is contrasted with nuclear devices, which are using like fusion and fission, for example, to create energy. And on the good side of that, we have our nuclear power plants, which is a clean way or a generally clean way of creating energy for all of us. And then on the other end of the spectrum, when people get a hold of certain types of radioactive material that release energy in this way, they could create like an improvised nuclear device, and that would certainly not be a good day for anybody. And then finally, explosives are our final category of hazardous substances. And again, we can use this commercially. When you think about construction or tearing down buildings or things like that, explosives are used on the day-to-day, normally safely in that environment. We have UXO, which I think about as like artillery from a military perspective that has been left out that if a civilian come in contact with will cause a lot of harm. And then IEDs, which are our improvised explosive device, which I'm sure you all are familiar with. Moving on a little bit to the chemistry aspect of things, I think this is definitely helpful when we think about chemicals more than anything. But we'll talk about some radioactive and explosive properties as well. Physical properties that are really helpful from a responder side is now, of course, there's like the initial event where you're just trying to figure out what's going on and what's involved. But typically, if you have a stable enough incident, you can appoint somebody to be a researcher for that event, and they are kind of actively working to identify the chemical and its properties and how can we use those properties to safely like recontain that hazard. And so physical properties, things like vapor pressure. This is obviously the pressure exerted by a vapor above the surface of a liquid. And we use that to describe the volatility or the tendency of it to vaporize. And so these are kind of directly proportional. Where you have a higher vapor pressure, it's going to be higher volatility. Um, when we think about like something that's very volatile, if it's going to have if it's going to vaporize, that's going to be more of an inhalation hazard than another chemical, for example. And that may mean that we have to adjust how we protect ourselves if we're the hazardous materials technicians going into to contain the hazard or stop the leak. Boiling point obviously is at which point we go from a liquid into a gas, and knowing when that is going to occur, what kind of environment that you're in is super helpful for the same reasons I described about vapor pressure. If you're in -20 up near the Arctic or like during the winter, how that chemical is going to react and how you might have to deal with it or consider containing it is going to be a lot different than when you're near the equator and it's a hot summer day. Um, Vapor density is how we judge the density of that to the surrounding environment. Um, I think about that in the sense of, is this vapor going to kind of sink towards the floor, or is it going to be rising higher up, either into the atmosphere or closer to like where I'm going to be breathing it in? And again, using that to judge how we go about clearing that hazard or containing it. Then we also have like evaporation and expansion ratios. Evaporation is just the speed at which it vaporizes in comparison to like a reference, and then expansion um, is for gas specifically. Um, it measures essentially the volume of gas when a unit of that evaporates, and is really helpful when you're thinking about like propane releases, for example. Moving on to chemical properties, these are inherent to whatever the hazardous material we're dealing with. Is it something that's going to be flammable? Is it something that poses an inherent toxicity, which is it going to actually harm me if it gets in here? And how much? What's the degree of that? Acidity, is it going to donate protons into a solution? But again, if we think about for those of us who are kind of on the healthcare side of things, how do we deal with acid chemical burns versus those that are from alkali are different. We have to worry about different things, and so it's important to know that. And then how reactive is that substance, which is the propensity of it to undergo a chemical reaction. Now, on the opposite side of things, when we're thinking about radioactive materials specifically, there are a couple of things that are really helpful. And I'm happy to talk more about radiation. That's kind of out of all the hazardous materials, one that I um, love to talk about and dive deep into, specifically as it causes harm from a medical perspective. But knowing if you are able to know a type of radioactive substance that's been released, knowing how much the rate of decay. So obviously, if it has a high activity, there's going to be higher levels of radioactivity that you're going to be exposed to potentially. Oop. Half-life, also very, very important. That's the length of time it takes for half of the atoms in a sample to decay. So if you have a radioactive substance that has spilled from its container that you're dealing with in the context of a counterterrorism event, um, knowing that if it's going to take 1,000 years to decay and meet half of the activity that it was initially, That's a whole different thing than something that, when released, is going to just rapidly decay and no longer be radioactive in minutes or hours or days. Um, when we think about decay specifically, you have the radioactive substance, but of course, when it is decaying, meaning it's releasing energy or particles to become a more stable isotope, um, we can classify that as, and there's some kind of subtypes, but in general, alpha, beta, and gamma. For alpha radiation, essentially, if you have kind of seen or can think about a helium atom, which is two protons and two neutrons, that essentially gets released. Beta, which is just the emission of an electron, essentially, or gamma, which is, we kind of separate that out and think of it less of a particle but more of a wave. Um, and they call it kind of electromagnetic radiation, but essentially more of a wave and not something that is deposited, or an actual like particle of itself. And that's important because alpha radiation, for example, super heavy in comparison to like a small electron, right? And so that's going to pose a huge hazard when you think about, did I get radioactive material in my GI tract, and that can wreak havoc on that. And that's a very different story than gamma, which is harder to protect against, but is radiation that goes through, um, and not necessarily something that you have to ingest, if that makes sense. And this kind of diagram goes to show how much it takes to actually stop this radiation. And when you're dealing in an emergency management situation of how do I protect the public from this, what are the recommendations that I'm going to provide, particularly with people that are far out from an incident who are still going to be worried well. If you think about a radioactive substance that is primarily an alpha emitter, so releasing those big heavy particles, um, the good news is that even though those can cause a lot of harm, because they're heavy, they don't travel very far, and even a sheet of paper or the top layer of your skin can stop it. Um, Beta is a little bit, takes a little bit more. Generally, a thicker sheet of aluminum will be what's required to stop it, because you have those like fast, tiny electron particles. And then finally, when we think about gamma radiation or those waves, it can take a decent amount of lead and shielding to prevent radiation from going through. And these can travel for miles and miles depending on the degree of the incident involved. And so obviously you have to think about um, the exposure net of the people that you have to protect. All right. And then finally, explosive properties. I will say these I feel like are less helpful than the others because typically in the context of dealing with explosives, at least from the civilian side, you are probably dealing with the explosion after it has occurred, and so knowing these properties are less helpful. But if you are somehow dealing with a explosive before it has detonated, or you're like thinking about it from an industrial sense of responding to a plant that has a lot of these in stock, if they're using it for, again, construction, for example, it might be helpful to kind of have this information. So velocity of detonation is like how far is that shock wave, the stuff that's going to cause blast lung and rupture your eardrums, how far and how fast is that going to travel after it detonates? The pressure is really like, again, the peak pressure of that shock wave, and that's going to determine what kind of injuries that can cause. Our auto ignition temperature, which is the lowest temperature at which it's going to spontaneously ignite. And again, our environment is super crucial to consider if we're dealing with an explosive. Sensitivity. There's a lot of different types of explosives, could do a whole different lecture on this, but something that is very sensitive might just take a little bit of a bump or picking it up off the ground, just the tiniest bit of friction, and it's going to detonate versus something that I'm trying to think something about more stable, like C4, for example, where you can, toss it in your hand, and it's not going to just rapidly detonate without having kind of a primary explosive on there. And then brisance is really just a shattering capability of a high explosive. and that is dependent on the pressure. So going into what I would think is kind of the most important part is how do we actually recognize that an incident has occurred? Thinking about labels, while this is kind of a graphic by the U.S. Department of Transportation, these classes are defined by the United Nations, and so I think is probably going to be pretty applicable, um, regardless of where you are. But obviously, there might be some geographical differences, depending on who's on the call. But this is really how we can, from a transportation aspect, figure out what exactly is going on and how can we like initially respond to a hazmat incident, even if we don't know the specifics of a particular chemical and don't know all of its properties. There's 9 classes here, as you'll see. We have class 1 being explosives, and there's all sorts of subcategories that if you're interested, you can kind of delve into. We have our gases, and those can be flammable, non-flammable, inhalation hazards. Similarly, we have our flammable liquids, and combustible solids, which are typically, those red triangles. You'll see a lot of those. If you've never thought about hazardous materials in your daily environment, I guarantee after you start seeing these placards when you're going down the highway, you will quickly realize that you're seeing a lot more of this on the road or near your railways than you previously thought. Um, Moving on, class 4, we have our solids. We have oxidizers, which I said are particularly bad. And dangerous there. Things that are particularly toxic are class 6. We have our radioactive substances. There's a couple of different subclasses that are not displayed here, but I'd say that's good enough if you see a radioactive placard. Um, Corrosives, and then there's a lot that gets dumped into this main miscellaneous label. But typically, when you have all of these different labels, you generally will also kind of in the middle of each one have an area that is blocked out and it has a 4-digit UN number. And that can be really helpful as there's apps and books that you can use to determine what exactly is going on. So, for example, we have this sort of accident that has occurred here, and you can see that at the back, and it's typically on the back and on the sides per regulations, but you have this Class 8 placard here. So you know that whatever is in this like 30,000 gallon highway container here, that it's has some corrosive properties. And you can use that 1760 digit to look up that further and identify what's going on. And I'm kind of jumping ahead of myself a little bit, but if you're not familiar with the Emergency Response Guidebook, this is from 2020, but they update it pretty frequently. This is where you can go about actually identifying what hazardous substance that you're dealing with. It's color coded. There are sections to identify based on the number. So you can look up 1760 and figure out exactly what that is, and it'll point you then to which guide you can use to do your first actions if an incident were to occur. Or you can actually identify it by the name itself and then are able to kind of backtrack and find the number and again the guide that you would use. Um, at least within the context of fire departments in the United States, this is like the gold standard for how you go about responding to a hazmat incident. And then moving along to some other labels, if you aren't familiar with the GHS system, these labels you'll definitely see if you have worked like in a lab or in a workplace. These are things that are not necessarily within the transportation realm. We generally use those other labels for those big highway containers, but you can find these GHS classifications on if you're responding to like a workplace or an industrial site. You can see here like pretty self-explanatory for what they mean, even if they don't have the actual label. Explosives, you have that shattering material, flammable, obviously has a flame. And then similar to that first, those other labels that I showed you earlier, the UN classification, the O with a fire over it generally always implies that an oxidizer is at play. Moving on, we have our corrosives, which are kind of similar. It looks like a little test tube that is pouring out and causing harm. Compressed gas, so you see that cylinder there. And then skull and crossbones is similar to our other classification as well as being reflective of toxicity. Stuff that's a little bit different, you see here the big exclamation mark that defines an irritant, which again, like implies it's health hazard. Carcinogens, which kind of looks like a bullet through the chest or the heart, but things that can cause cancer. And then a fish with a tree kind of reflects that aquatic toxicity. And again, if you're on the environmental side of this or dealing with a hazmat incident out in the wild, that would kind of give you some more information about am I close to a body of water and do I need to care about this particularly causing damage to wildlife? And then finally, again, going through a lot of different things of how we can recognize hazmat. The NFPA 704 system, that's that same organization that provided the definition that I talked about at the very beginning. But you'll typically see these on large containers or storage facilities. So this is not transport typically. These are things that are like stationary facilities or containers for different hazmat. And so this looks a lot more complicated than it is, but typically you have red, which indicates a fire hazard, blue for health hazard, and then the yellow for instability. And then not on every hazmat, but you can have different codes or symbols within this white that indicates if there's a special hazard that's present. So within a facility that may have like one or more hazmat that you might have to deal with, they'll have this triangle on the outside of that facility, and there will be a number in each of those. And this is essentially what it means, but all to say that the higher the number, the more dangerous and more cautious that you should be about it. And as you can see, for example, a fire hazard of 0 is a hazardous material that won't burn, versus 4 is something that's going to rapidly vaporize just at our atmospheric pressure and burn readily. And those are two very different hazards. And so you can kind of see the other classifications, but in general, the higher the number, the worse. Moving on to containers a little bit, because we've talked about these labels that are on the outside of it, but how do we use containers themselves to help us out too with recognizing an incident? And all of these images are kind of pulled from this ERG. So if you're looking for reference or want to dive deeper into that, would reference that book. Um, you have the DOT 406. This is essentially every container or every truck that you've ever seen on the interstate that is carrying gasoline that's going to stop and refill at a gas station. There's certainly exceptions to that, but you will see these probably most commonly in your day to day. It has that really oval shaped kind of cutaway view from the back versus the DOT 407, which is a lot more circular. It can have a covering over it that looks a bit like a horseshoe shape instead of circular. But in general, when they're unhoused, will be completely circular like that. And you can see how like the capacity of these things differ a little bit. DOT 412, this is kind of where I get into how we can use this container to help a little bit. These almost, I don't want to say almost exclusively, but largely will be used to transport corrosives. And so when you see a little bit of a ladder on the side and this additional kind of hardware like this, you can almost guarantee without seeing a placard that you're at risk for having a corrosive material in there. Versus these kind of material or this kind of container, our dry bulk cargo container, which is going to contain things that are typically solids. And while it's stored in this sort of trapezoidal container, it has these little outlets on the bottom where that solid substance is able to be like drained out from. Moving on a little bit, our MC331. This looks like pretty much a cylinder or hot dog. Um, this is because we're containing gases under really, really high pressure. They're typically white, and again, like these kind of end caps are rounded. It looks like a hot dog, literally. And that's just to help again because you have compressed gas, and so you need to have those smooth substances there or surfaces. And then finally, with our MC338, these have what looks almost to be like a cabinet on the back, and typically these have cryogenic liquids in them. Then when we move on to rail, we have things that are pressure, like hazardous substances. Again, similar to ones that are contained on highway, but just a different container. These is kind of like what the housing looks like for substances that are under pressure versus on the right, it looks a little bit different. These are low pressure or non-pressure. And that kind of helps with like how far do you need to stand back if this thing were to rupture. Um, but you can kind of see how the housing differs. One has this like protective case around it, and this one doesn't. Um, and then there's a few other ones than what I've depicted here, but similar to what we talked about with highway containers. You have a cryogenic tank car, and then you can have hopper cars, which will likely carry those solids and again can like drain out from the bottom. And then finally, intermodal containers are what look to be like these white sort of tubes, similar to the ones like the MC331 with that compressed gas. They're just a lot smaller and they have this protective casing on it, these frames, and these allow them to be stacked either on if they're going to be transported by rail or on shipping containers like boats and stuff. These can be stacked on top of one another. And they're a whole nother beast, but again, can carry a variety of hazards. So finally, kind of moving on into response principles. Um, RAIN is the one acronym that would say that you need to remember, especially if you're thinking about about being in a capacity to respond to a hazmat incident. One is that you need to, again, recognize that a hazmat incident has occurred. If you don't recognize that one has occurred, you can't do any of the other steps. You can't activate the appropriate people to respond to an incident. So that's why you got to use containers. You use the labels that we talked about. You use hopefully not smell, but sight, hearing to kind of recognize that something bad has happened, and that there might be a hazmat that has released itself and might be a harm to the environment or the people around it. The next step, once we've said, oh crap, something bad's happened, is how do we avoid the area? How do we create some protective distance between ourselves? The general principle is that you want to stay upwind, uphill, and or upstream from the hazmat because it's all gonna go in that one direction, and you kind of want to stay away from that. Um, what's really helpful, and we'll go through a bit of a case study, but this, like I said, has for whatever guide that you have, it will give you the initial protective distance. Now, that's not going to be the whole hot zone, warm zone, cold zone kind of distancing, but it's like within the first 30 minutes of an incident, here's how far you should stay away. And each guide that you have within this book will just give you those general recommendations that can be life-saving. Um, and that's kind of with regards to that isolate too for finding those initial distances once we've learned how to best isolate or avoid the area. For radiation specifically, I think it's important to bring up the inverse square law. And that is essentially that when you double your distance from that radioactive material, you're going to cut down your exposure in half. And that's critical that just by going from 2 feet to 4 feet away, you've cut down how much radiation you're going to be exposed to. And that's going to be crucial, particularly if you have an isolated substance that you know what you're dealing with and it's not actively being spread out towards you. And then finally, N is for notify. And whether you have an explosive incident where you might need to call law enforcement if they have your jurisdiction's bomb squad is going to be very different from calling your county's hazardous materials response team because you have a chemical incident on the interstate. Mentioned this briefly, but once you have those initial actions down cold, You've established incident command. We can start thinking about establishing zones and how we're going to deal with this. Obviously, our hot zone is where the actual hazard is and where there is contamination. Warm zone, ideally, is where you can provide like very, very life-saving emergency care. Um, nothing too technical, just like the bare bones of, stopping bleeding, for example, can be performed. This is where, ideally, at the jurisdiction between, or the junction between the hot zone and the warm zone, you have a corridor where you can control contamination and ensure it's not really getting tracked out to the warm zone too much. And then finally, you have your cold zone, which is where you're going to stage your incident command, medical care, um, and then ambulances for bringing people to definitive resources. If you are in on a team that's going to be responding to a hazmat incident, there's a couple of different types of PPE that you can wear. Starting with level A, this is our highest level um, gear that you would wear, and typically this is reserved for substances that are vapor hazards. So this suit is all encompassing. It protects against vapor, like from penetration of vapors towards your skin. And you can kind of see here, although there's a bit of a glare, that this person's wearing an SCBA, self-contained breathing apparatus. And so they have their own oxygen supply within this encapsulating suit. And this is like the highest degree. Um, if you have the highest hazard, you would be wearing something like this. One downgrade from that is our level B PPE, which is you have the same breathing apparatus. They have their own oxygen supply with a tank on their back, but um, you'll see that this suit, you would kind of wrap it around your face mask. It's not all encompassing. You're essentially putting on the suit and then putting your SCBA over it. So if you have something that's a vapor, it's not going to protect you all the way, but it is generally a pretty good method of protection for a lot of different substances. Um, Working down a level is C. You again have like a pretty good chemical protective suit here. Our main difference is that we have a lesser degree of respiratory protection. This has a filter on it, rather than your own breathing apparatus, which is probably great for mobility, but you have to take into consideration you have to know your hazard. Do you have the appropriate filter for that? Is there enough oxygen in the environment that isn't saturated by this hazard that I can still breathe and keep myself conscious? Things along those lines is kind of what you have to know to have a level C. So there has to be a good degree of research into knowing your hazard before you go ahead and choose that. And then finally, level D here. This is kind of our work gear. It doesn't have to look exactly like this, but it's just our lowest standard of protection. Um, and then when we think about decon, a couple of different ways or a couple of different methods, and what each re which what each agency or resource has. As far as the tools that were actually going to be needed to conduct this is going to vary so widely. But in general, if you are dealing with hazardous materials technicians who are wearing these kind of suits over here, when they get out of the hot zone and you're going through that contamination corridor, you would do something like a technical decon, and you have a big line of showers and you have brushes to scrub down, and it's a very methodical process of removing contamination before they actually go about taking off their SCBA and their suit. Versus emergency decon, this is like, hey, I have somebody in a suit or even just a civilian in their day-to-day clothes, and they um, kind of rapidly need to have uh, contamination removed from them so that they can get into medical care ASAP. They can't wait to go through a more technical decon. It's like, hey, we just got to wash this off and get them to definitive care. Then finally, mass decon is how do you deal with deconning uh, 5,000 people that were at a stadium that got exposed to some substance, usually civilians in this case, but what kind of resources are we going to have to funnel all of those people into getting deconned? How are we going to clothe them afterwards? Um, what kind of resources do we even have to like rapidly get this stuff washed off is going to be critical, and again varies a lot by where you're at. And then um, finally, I think it's just important that regardless of your resources, there's a lot of people that can help and that are available within North America specifically. And again, the ERG has all this information in it, has all these phone numbers to where if you have looked at a like semi trucks shipping papers and you know exactly what hazmat you're dealing with, or you have just enough information that you're overwhelmed but you need a little bit more help, you can call any of these organizations, these resources, and they have experts on the line that are helpful and will ask you a lot of questions and try to get more information so that they can help you with the specific information about that hazard so that you can respond appropriately. And a big shout out to REACTS or the Radiation Emergency Assistance Center. This is a worldwide resource. It's located in Tennessee, but they have a physician and a nurse on, I believe, 24/7 that if you're worried about exposure to radiation or have an incident, they will help you out, particularly with the medical aspects of it. And then finally, some helpful apps. I've mentioned about a million times. I think the ERG is great. There's an app version, there's a physical version. The NIOSH Mobile Pocket Guide, we didn't talk a whole lot about that, but it gives you a lot more chemical information, more for any particular hazard. It gives you a lot more specific information about that hazard, which will help you if you're kind of in that resource role of how can we use different properties to help guide our response. Similarly, Cameo Chemicals is an app that has a lot of that similar information and can help with determining distances and PPE and all that. Ask Rail. If you are in a jurisdiction where there's a lot of railroads, you can request access to this, and it'll show you if you get approved and such. It'll show you what each container on a given train is carrying, so that if you're involved in an incident, you can rapidly discern what is each in each container and how do we respond to that. And then within radiation specifically, there's a couple of apps that you can use for determining dose and thinking about or estimating dose, and then like how are we going to respond to this from a medical perspective. And then finally, just moving on to a bit of a case study to put all of this together. Um, for this, you're called to the scene of a multi-vehicle collision on the interstate, and as you approach, you see an unknown liquid leaking onto the asphalt from the truck below. And if any of y'all want to, if you have access to the ERG, happy to drop the stuff in the chat. Otherwise, I'm happy to just kind of walk it through with you. But you see this placard on the back of it. Um, what is this? Does anyone want to give any ideas on at least what classification we're dealing with here? No, that's fine. I'll go ahead. Um, so for this, obviously we have kind of similar to the one I showed earlier. You can kind of make out an 8 here, maybe those test tubes, the black and white. For this, I would be worried about a corrosive hazard. And if you look, you have the United Nations number 2582, which you can rapidly look up. And for this, we're dealing with ferric chloride, which is again a corrosive substance. Stepping back a little bit, this was our container. Anyone remember which one that was exactly? You can kind of tell based on what we talked about, there likely being a corrosive in here. But you see this staircase kind of going up to the top. We have our rounded image from the back. And if you didn't have this placard at all, I would be worried that this is a 412, which typically carries corrosive substances. And so now that we've kind of discerned what our hazard is, and you're like, oh crap, I'm the first fire engine on scene. How far do I need to get away from this? Or do I not? Is it just water? Um, you have all this information about it being ferric chloride. And so when you go through the ERG, for example, it'll say for this substance, flip to guide 154. And then you can kind of scroll down, go to evacuation. And it says isolate the spill or leak area in all directions for at least 150 feet for liquids or at least 75 feet for solids. For this, it's like, okay, let's try to get all of our car accident victims. Make sure our police, our fire responders, our EMS, that we're all at least at bare minimum, whoever is on scene, at least 150 feet away. And then as we think about a little bit further down the line, if this were to, because you have a leaking container and you have hazmat technicians available that are going to be able to approach the scene and stop the leak, what kind of PPE would you recommend that they go about using? And for this, usually a little bit more research will be helpful for you, but it doesn't hurt to be safer than sorry. But the first thing that you can kind of see within your initial guide on the ERG, if you hadn't called anybody else about this and this was all the information that you had, you can see that under health for this kind of class of substance, that it is toxic and that inhalation, ingestion, or skin contact can cause severe injury or death. So if you didn't have any other information about ferric chloride, you didn't have internet access, and you're like, this is all I'm dealing with, I might consider like a level A. Um, Probably, I doubt that you would really know what filter, unless you had like a general broad like chemical filter. I might be more worried about like needing to use a level A or B, but if it's gonna be if all that you have is that this is toxic and that even skin contact can be dangerous, I'd probably want to err on the side of using a vapor protective suit, so a level A, until I had more information or we had the scene secured and stuff like that. And then, kind of the final part of the case study here, while you're working to stop the leak of the hazmat, one of the technicians loses consciousness and falls to the ground. It's 100 degrees Fahrenheit outside, which is very hot. And the partner is able to extricate that technician to the border of the warm zone. And so, what kind of decontamination would be performed on the unconscious technician versus the one performed on the partner? And there's only a few guesses to choose from here. But this unconscious technician, we don't know if they got overheated or had a cardiac event or got exposed to this substance, but regardless, they need immediate medical attention. And so for this, I would probably perform an emergency decon. Let's hose them down really quick, get them out of the suit, get them taken care of, versus the partner, who assumedly is okay, after kind of performing that extrication, but they're ready to get out of the hot zone and they want to be decon too. And so for this person, I might consider doing that more technical decontamination where we methodically have the time and resources to scrub down the entire suit, make sure it's very uh, appropriately washed off, and that they can kind of slowly take off their hazmat suit appropriately once they're done with their run within the hot zone. And so, in summary, I know I've been talking a lot, and I hope that this has been helpful, but hazmat are substances that, when released, can cause harm to people, property, or the environment. And that if you have the information available to you, knowing the physical and chemical properties can let you know how it's going to react once it's released, and how we can structure our response to that. I think a lot about some of the activities that we do when you're training to be a hazmat technician. If you have a hazmat that is kind of mixed into a stream and you're trying to create a dam to isolate that substance, knowing whether it rises on the top of the water versus the bottom is helps you guide how you would structure that dam so that you can let the normal water keep running, but you're isolating that hazardous substance. Of course, we talked about a lot of vapor properties too, but that's the one that stands out to me a lot. Um, Within the US specifically, or if you're in a nation that uses kind of that UN classification, we divide hazmat into 9 different classes. at least within like the chemical hazards. Using labels and shipping papers will provide that additional information to where you can look it up more and help structure your response. But if you're just the initial responder, using that RAIN acronym is going to be crucial to just making sure that you can kind of protect the incident and get help involved and hopefully not hurt yourself in the process. And then we talked a little bit about PPE too, and how you kind of structure which one, because all of them can be kind of, or especially the level A and B can be quite expensive. Um, what one do I need to use to protect myself or responders appropriately when they're responding to an incident? And these are my references. And yeah, that's about it. I know we have about 8 minutes left. Happy to take any questions that you have, um, or just talk about hazmat in general. Yeah, I see somebody with their hand raised. Go ahead.
Hi everyone, can you hear me?
Yeah, we can hear you.
Hello, well, my name is Enrimar. I'm a third year med student of the Central University of Venezuela. And I would like to make a question because a couple of years ago we had an accident involving a gas leak from formaldehyde, which
Hmm.
we use here on our college for cadaveric material for anatomical purposes. So mostly I would like to ask, will this qualify as a hazmat in that case? And also in Venezuela, communication between agencies like the fire department is quite slow. So what immediate recommendations would you give to a group of students to resolve this situation when basically we are the only ones available to handle it?
Those are two really great questions, and thanks so much for sharing your experience. Definitely, formaldehyde, having worked with it in medical school, is definitely a hazardous substance, particularly because you have a release of it. If you look a little bit more, I just typed it into the ERG, but um, has both corrosive and flammable properties. And so when you have a substance like this that's known to be particularly toxic and it's been released from whatever container, if you're working in a lab or some anatomy dissection lab, whatever, definitely would be a hazardous materials incident. Now, whether it would be the same type of incident as um, I don't know, a terrorism incident where 50,000 people are affected versus just like a tiny spill within a lab, those responses are going to vary a lot. And of course, your resources within Venezuela are probably going to be a lot different than um, mine in Cincinnati, for example. There's a lot of variation there, but it's definitely a hazmat incident. And as students, I think that's a tough role. Usually, and I can only speak to my experience, so there might be some limitations here, but um, typically there is somebody within an institution. If it's like a lab incident, for example, there's like a lab manager or a safety manager within a lab who's generally involved in that. I'm not sure if you have that, but
We don't.
no, okay. It's hard to give you specific guidance about how to
Of course,
better
I understand.
coordinate between those agencies, but I think alerting, depending on like the degree of the incident and your protocols within the institution that you're at for cleaning up or responding to those, it's really just going to be escalating it to the professionals that are trained to handle it. And I know that's a very vague answer, but there's a lot of what ifs in there.
Yeah, I understand. Well, thank you so much.
Yeah, thanks for asking. Any other questions or comments? I see y'all have been responding to this in the chat. It's hard to see on my screen when I've shared, so I appreciate your engagement. Here's one. So from Pauline, concerns have been raised in our northern Ontario city about a proposed plan for transporting spent fuel from nuclear power plants in the south to a facility in the north. The route runs through a significant leak of the center of our city. There would be 2 to 3 truckloads during the day of an accident or spill. Yeah. And how should the city emergency? That's a great question. With regards to spent fuel from a power plant, I'm not as super familiar with those. I assume it's like spent uranium, for example, but um, I'd have to look a little bit more into the specific aspects um, of that substance. But I think um, folks have the right to be a little bit concerned when you're having big loads of hazmat run through an area, particularly if there's people walking about and it's not like an industrial kind of isolated highway or interstate. The best thing that you could do from just an advocacy perspective is engaging. I think the best resource, as opposed to just like the hospital, for example, which I'm sure there's a radiation safety manager on site that deals with the hospital's internal emergency response, is to talk with your city's, not just the emergency services, but if there's a city or a county emergency management agency, they will certainly have protocols for how they respond to pretty much an all hazards incident, regardless of whether it's something like a tornado or a hazardous materials incident like this. And so, if this is like a newer, yeah, you said it's like a proposed plan. I think it would be worth if you have connections to city council or whoever is kind of proposing this to get the perspective of the emergency management agency that's within the city or the county or province that you live in to provide some insight onto the specific hazard from that power plant, how much is going to be transported and the frequency, and how they plan to, honestly, more than anything, respond if there were to be an incident. Um, I'm sure there is somebody behind the scenes that's like, hey, if something were to happen, this is what we would have to do. But sometimes that can get kind of overshadowed for industry, at least from my perspective. And so, um, definitely advocating to learn more about response plans and how the city plans to protect against that is going to be critical. But thanks for asking. That's a really interesting scenario. I know we just have 2 minutes left. Any other questions that I can answer for y'all or anything that you want to chat about? No? Well, if not, thank you so much again for attending. This is a very technical lecture. This is just like a very broad blanket overview for hazmat. If you're interested in actually talking about different substances, the more medical aspects of that, let us know. Happy to come back and do this another time. And again, if you are interested in getting involved within our interest group, Andrew has dropped a link in the chat a while back to where you can sign up and get our email list and get kind of more newsletters for future events like this. Thanks so much.